This presentation is the third lecture in Unit 4. It's titled Where Are My Electrons? Here you see it says, without electrons there is no Google, and without clean electrons there will be no Google customers, since we'll all be too busy fleeing from rising seas, droughts, and disease. So the learning goals for this presentation are that students understand the octet rule. Now you should have a general understanding that octet means 8. And that electrons exist in orbitals and sublevels, and you should be familiar with the Aufbau principle. Now, this is actually going to be a little bit more specific version of the Aufbau principle than the previous one, the Pauli exclusion principle and Hund's rule, and that you should be able to tell, or you should be able to relate the electron configuration of a particular atom to the periodic table. So, here's what we know. Electrons can transition between the ground state and the excited state. We've talked about that several times. We've referenced it several times. We also know that the absorption and emission involves radiation, and we know that electrons tend to move towards the state of lowest energy, which we referred to as the ground state. Now, what we learned in the lab, we learned that electrons have more specific direction than just energy level. Electrons have a specific quote-unquote address that depends on several different factors. In fact, we use the term, I believe, quantum numbers to refer to the address of a particular electron. Now, the first thing we need to do is we need to talk about the experimental evidence that led us to believe this idea of suborbitals, and that's an experiment that's called the Zeeman effect. Now, if you were to take, this is a spectrum line, so you know how we had hydrogen and it had spectrum lines here, 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 and here, okay? They took these single spectrum lines, and what they did is they actually exerted a magnetic field on the particular object. So what you see here is a north and south. It's a north magnetic pole and a south magnetic pole, and they put that single line spectra, the single transition, into a magnetic field. And when they did that, they saw that this single line split into three very, very, very closely spaced lines. And it was actually very difficult to see that there were three different lines. So what we said is a single spectrum line, when you put a magnetic field to it, actually turns into three very, very, very closely aligned lines. So that provided evidence that we had that not all, when you have a magnetic field, that there are three different energy levels. And so what we now know is that we have something what's called the p orbital. In this p orbital, when you put it in a magnetic field, part of it will align with the magnetic field, lowering the energy. Part of it will oppose the magnetic field, raising the energy, and then the third one is perpendicular to the magnetic field, so it has no effect. So what this led us to believe is that there is something called suborbitals. So now we know that there is something called a suborbital. It's not just a 1 or a 2. So the first one we have, the first suborbital that we have is called an s orbital. Now, the s suborbital has a maximum of 2 electrons, and it obtains this spherical shape. Now, with all orbitals, when we look at the quantum model of the atom, we don't say that the electron is in the sphere. What we say is that there is a 90% probability of finding the electron in this particular sphere. Now, the s orbital on the periodic table actually references, if you look at the periodic table, references these first 2 columns are s orbitals. So if you were to look at the valence structure of an atom, or an electron, we're not there yet, so you don't know what valence is, everything in these first 2 rows represents something that has an s orbital as its last orbital. Next, we have what is called the p orbital. The p orbital starts at the second energy level. Now, if you notice, there's no p orbital on the top one because there's only 2 elements. Now, the p orbital can hold a maximum of 6 electrons. It can hold 2 in what's called the pz, 2 in the py, and 2 in the px. So because of that, each one of them can hold 2 electrons for a maximum of 6. So you have a 90% probability of finding the electron, and what this references is these groups on the right side of the periodic table. Groups 13 through 18 on the periodic table, if you were to look there, their last electron orbital would be a p orbital, so you can see that right there. Now, whenever I said in the second energy level that it can hold a maximum of 8 electrons, it could hold 2 in the s and 6 in the p for a total of 8 electrons. So next, after the p orbital, we can say that whenever you add the 2 from the s orbital and the 6 from the p orbital, that adds up to 8. Well, that means that an atom has a complete orbital shell if it's less than 36 atomic number, it has a complete orbital shell whenever it has 8 electrons in its valence shell or its outside shell. So because of that, we say that these things are stable when they have 8 valence electrons in the outer level, because it really doesn't want to take another one on, because if it takes another one on, it has to add another level. It doesn't really want to take or lose one, because if it loses one, it can take one more on. So we say that atoms are satisfied when they have 8 electrons in their valence shell. Now, you also have, for elements that are larger than 36, you have things like the d orbital. Now, the d orbital starts at the 3rd energy level and can hold 10 electrons because it has what's called, you can't do x, y, and z anymore because there's 5 of them. So we say d minus 1, minus 2, 0, 1, and 2. So what that tells me is that there are 5 different orientations of this particular d orbital. Now, once again, the orbital represents the 90% probability of finding an electron. Now, the d orbital, if you were to look at the periodic table, represents these right here, what we call the transition metals. Okay, groups 3 through, 12? Groups 3 through 12 represent that. So those are anytime you look at a transition metal, what gives some of those things some unique properties is the fact that they do have d orbitals. The last orbital that we have is the f orbital, and it starts in the 4th energy level, and actually can hold a maximum of 14 electrons because each one of them can hold 2, and there are 7 in f minus 3, minus 2, minus 1, 0, 1, 2, 3. It represents a 90% probability of finding an electron. Now the f orbitals, if you were to look at a periodic table, okay, are these pulled out section called the lanthanides and actinides. Everything below here, if you were to look at its valence structure, would be in the f orbitals. So that's why the periodic table has this crazy shape. You see s orbitals right here, p orbitals right here, d orbitals right here, and f orbitals right here. They're pulled out, and the shape is according to the orbitals that they have. Now, one other thing that's kind of strange, and you'll notice this quite a lot, that hydrogen and helium tend to be strange. Sometimes it is appropriate to put hydrogen over here. Sometimes it is appropriate to put helium over here. So just be very careful when you're trying to draw conclusions about helium. In this particular case, when I'm referencing the orbitals, helium should really be right here, because it is considered to be an s orbital whenever you look at it that way. So, how many electrons can exist in each orbital? So, for example, you have d minus 2. If you look right here, I have d minus 2. It can hold 2 electrons. This can hold 2 electrons. This can hold 2 electrons. This can hold 2 electrons. And this can hold 2 electrons. So, because of that, the d suborbital can hold a maximum of 10. But d minus 1 can only hold 2. What connects these is the fact that there are 5 d suborbitals. Now it says which suborbitals are present in the energy levels 1, 2, 3, and 4. Now if you were to look at the periodic table, it's pretty evident that in the 1st energy level that there is only the s orbital. Now if you were to look at the 2nd energy level, the 2nd energy level has both s orbitals right here and p orbitals right here. Now, 3 is very, very tricky at this point. And the reason why is we'll look at with the Aufbau principle in just a second. But this right here is considered to be the 3rd energy level. I know it's in the 4th column, okay? Or excuse me, it's in the 4th row. But this D section is actually considered to be in this above orbital. Okay, and we'll talk about why a little bit later, but for now, just go with me that for the d orbital, so this 3 has an s, a p, and a d. Likewise, this appears to be way down here in the 6th energy level, but it actually goes up 2 and actually belongs in the 4th orbital, so s, p, d, and f. So basically, every time you add an energy level, you're adding a potential letter or suborbital. There are some books in college, 2nd, 3rd, 4th year chemistry, that will actually project outward past the f orbital. So they'll talk about a g and an h orbital. There are no real elements at this point that have ever been discovered that are in a g or an h orbital. So we are going to stop in this class at the f orbital. The mastery level question says the emission lines of a sample are put into a strong magnetic field and split into 7 distinct lines. What is the most likely orbit the electron is transitioning from, and to justify your answer using the clear method? Well, if you were to look at this, the original one that we had that split from 1 to 3 did so because it was going from an s orbital to a p orbital, where you had 1, 2, 3 suborbitals. So you had 1, 2, 3 potential transitions, so you got 3 different lines. Well, if I have 7 distinct lines, I'm going to need something which has 7 suborbitals. Well, the 7 suborbitals that are only possible in an f suborbital. So what I would say is that it is from an s to f transition. Now, the evidence that I have to support that is the fact that it goes from 1 to 7 lines. Now, the reasoning that I have for that is that it was initially in an s orbital because there was 1 line, and that it transitioned to 7 because there are 7 lines in an f orbital. This is the Aufbau principle. So the first thing that we said in the first video was that you fill the first energy level before you fill the second. Then you fill the third, then you fill the fourth, and so on and so on and so on. And that is for the most part true. However, there are some exceptions because of the energy levels in the suborbitals. So what happens instead is that the electrons are filled according to the order that's shown in this image to the right. Okay, what happens is the 1s orbital is filled first, and that is the entire first orbital. Then the 2s orbital is filled, then the 2p orbital is filled, and then the 3s orbital. So what you see is the whole first orbital is filled, then the whole second orbital is filled, and then we get to the third. And the third is where it gets somewhat tricky. It is more energetically favorable to fill the third s, the third p, and then the 4s before filling the 3d. So remember how we said on the periodic table that it's got this weird shape, and this first level of transition elements is really in the third, but it's shown in the fourth? The reason why it's shown in the fourth is because it is more energetically favorable to fill the s and then come back and fill the 3d than it is to fill the 3d and then go to the 4s. So that's the reason why it's shown in that particular order. So what you do in order to figure out what the lowest energy levels are is you just start off and you label 1s, 2s, 3s, 4s, 5s, 6s, and label them down. 2p, 3p, 4p, 5p, 6p, all the way down. And then you draw diagonal lines. Okay, this works out this way. So you would say this is the order that they're filled in. So I would fill in 3d, and then 4p, and then 5s, and then 4d, and then 5p, and then 6s, and then 4f, and then 5d, and then 6p, and so on and so on and so on. So this is the order that you fill the electrons in, and this is why it doesn't match the exact number of orbitals for each energy level, the shape of the periodic table. Now, the reason for this is if you were to take all these energy levels and you were to put them in what's called an energy diagram, you would see that 1s is by far the lowest energy level. Okay, so if I have like energy is increasing, then the next one is the 2s, then the next one is the 2p, and then you would see the 3s and the 3p. But then what you would see is you would see that the 3d is here, but the 4s is in between. And electrons always want to have the lowest possible energy, so they will fill in here first before they would fill in the 3d. That's the reason why you have this Aufbau principle. Now this is a byproduct of us knowing this. So this makes it easy, but it's not because we wanted to line them up and draw diagonal lines. It's because they have lower energy levels. Next we have Hund's rule. Hund's rule says that electrons exist in pairs, but generally speaking, according to Coulomb's law, electrons want to repel each other because they both have a negative charge. So what Hund's rule says is when you have equal energy levels, okay, equal energy levels, that it will fill one electron first before it will fill the second electron. Now, if you notice, I filled this one in first, and the reason why is the 2s energy level is actually lower in energy than the 2p. The 2p is higher in energy. So I fill the 2s first, and then I come through and I fill the 2p. And what the Hund's rule says is I will put an electron here, and then I will put an electron here, and then I will put an electron here before going back and putting a second electron in the first orbital. So one electron each in each suborbital until it has to double up. So this right here is an incorrect drawing because it shows two electrons paired up while you have these open spaces that are there. Next, we have the Pauli exclusion principle. The Pauli exclusion principle says that no two electrons can have the same set of quantum numbers, address. So you define the quantum numbers as this. Each one has its energy level. That's the 1, 2, 3, 4, 5 on the side of the periodic table that we talked about. Then every atom has what's called an angular quantum number. The angular quantum number just tells us the shape, S, P, D, or F. Okay, then every atom has a magnetic quantum number, which tells us is it X, Y, or Z, or something along those lines. Is it -1, or is it -2, -1, 0, 1, 2, like a d orbital? The last quantum number is the ms number. It's called the spin. Okay, the spin of an electron can be a +1/2, or it can be a -1/2 for each electron. Now, if you have two electrons that are in the same suborbital, like you see here, those electrons have to have opposite spins. And the reason why is this. If you think about these electrons, they are both negatively charged. So they would prefer not to be next to each other or prefer not to be in the same orbital because of Coulomb's law, they'd like to repel. But because of the energy situation, it is more favorable for those two electrons to be in the same suborbital. So what I do is I give them both +1/2 spins. Now you don't know this, but whenever you have an electric charge that moves, it actually creates a magnetic field. When both electrons spin in the same direction, they both essentially create two north magnets. Now, you know that they're going to repel each other because they both have negative charges, but if you put two of the same magnets together, they also repel. So I have two things that are trying to repel here, and that just doesn't work. If I were to change it up, though, and instead of making this a up arrow, I make this a down arrow, now I have a north magnet and a south magnet. They're still going to repel each other because of the negative charges, but what are a north and a south going to do? Well, they're going to attract. So you'd have one force that would kind of try to pull these apart, and one force that would try and pull them together, and that kind of negates it a little bit. It's more energetically favorable to have one spin up and one spin down. So you have electron diagrams. Electron diagrams are where you line them up from top to bottom according to suborbitals, and you fill the electrons according to the rules. Now if you notice, I have one arrow up, one arrow down, because that conforms to all the rules that we've set. Okay, one arrow up, one arrow down. You fill from the bottom up, the lowest energy to the top. So you see a developing level question. It says define the following rules. The Aufbau principle. The Aufbau principle says you fill the lowest energy levels first. Hund's rule says that you fill one electron in each before adding a second. The Pauli exclusion rule says for every orbital you have to have one up and one down as opposed to two that are up or two that are down. Okay, those are the definitions that guide how we put the electrons in. Now this one says draw the electron structure for nitrogen and justify your answer using Coulomb's law. So if you look at nitrogen, nitrogen has 7 electrons. Okay, I know that because it has 7 protons according to the periodic table. You can also look at the general shape of it. You can say that nitrogen has the first energy level is the 1s orbital. The second is the 2s orbital. Then we get to the 2p orbital, and remember the 2p orbital has 3 suborbitals. So I start from the bottom. I put one arrow up. If I have one arrow up, the next one has to be down. Notice how I filled the 1s completely before moving up to the next energy level. Then I would put an energy level or an electron there and an electron there. Okay, now I've filled the 2s orbital. How many electrons have I used? I've used 1, 2, 3, 4 electrons. So that means I have 3 electrons left for this last energy level. Now if you look, I'm going to put an electron here. And it actually doesn't matter if it's up or down. So if you're concerned about that, it doesn't matter. So I filled one electron up. But before I put a second one in this, I can't do that because that would violate Hund's rule. So now I come back and I put another electron there and another electron there. And what that shows me is that I've used all 7 electrons. Okay, so I've used my last 3. And this is the electron diagram, electron arrow structure for nitrogen. We have proficient B3. It says the orbitals px, py, and pz are said to be degenerate, which means that they have the same energy level, which will be filled first. So if you were to draw it out like we just did, we had 1s right here, we had 2s, and then we had 2p, and they were all the same level. Now remember, there's only differences in the energies between the suborbitals if you put a magnetic field there. Other than that, they're degenerate, they're going to be at the same energy level. Okay, a lot of people say, well, you fill the one on the left first, but there's no way of knowing which one is the left and which one is the right unless you put it in a magnetic field. So because of that, you don't know which one will be filled first. It's going to be random at that point because these are lined up, and so it'll fill up whichever one it gets to because they're the same energy. So now we can represent atoms. We can also represent atoms by their electron configuration. Now when we do this, what we're doing is we're saying this is the electron configuration for a particular element. Now you do need to be careful here because when we express the electron configuration, sometimes atoms can gain electrons or lose electrons, and so the electron configuration could be different for ions. So just keep that in the back of your mind. But what we do is we just draw out the electron configuration. We say this is the energy level, this is the suborbital, and this is the number of electrons that are present in that suborbital. So you see hydrogen is simply 1s1. Now fluorine's a little bit more complicated because fluorine has 9 electrons to deal with. So in the ground state, we filled up the 1s with 2 electrons, hence 1s2. Then we filled up the 2s orbital with 2 electrons, 2s2. And then finally, we had the 2p orbital, and we filled it up with a total of 5 electrons, which make it the 2p. So fluorine is 1s2, 2s2, 2p5. Now you can represent all these atoms fairly easily by filling the electron configuration, or you can look at the periodic table. But we want to look at a shortcut because it's pretty tedious to write out all of the electron structures. So whenever we look at potassium, it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and that's just potassium. Potassium's 19. When you start to look at elements that are like 100 or 92, it tends to be really, really long. So what we came up with is what's called the noble gas shortcut. Everything that ends with S2P6 represents what we call a noble gas. So instead of writing out the electron configuration for that particular noble gas, we write out what that particular element is. So this right here is a total of 18 electrons, which is the noble gas argon. So I just write argon and then what is after argon. So you have to use the closest noble gas, but the one that's before it. So for example, if I was trying to do fluorine, which we did in our previous example, I could write hydrogen, and then I could write 2s2, 2p5. That doesn't really save a whole lot for fluorine, but what people tend to do, or they make this mistake, you should not do this, is they try to say, okay, well, fluorine is closest to neon, and they say neon minus 2p1. And you can't do that. Okay, you got to start off with the one that's before it. I should say helium, not hydrogen. Okay, you got to start off with the one that's before it, not the one that's after it. So now developing, it says write out the appropriate nuclear symbol notation. Now this is review. And electron configuration for a non-ionized atom below. So the first thing we do is we look at the number of protons and neutrons. So I have 1, 2, 3, 4, 5, 6, 7, 8 protons. If it's 8 protons, I know this is an 8 and an O. Because the atomic number is 8, means 8 protons. That's an ugly 8. So when we write 8 protons, the next thing we do is we look at the number of neutrons. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 neutrons. So we would put an 18 right there because that represents the atomic mass, the number of protons plus the number of neutrons. The next thing we say is it's non-ionized. So since it's non-ionized, there is no charge right there, so we don't have to put anything there. So this is the nuclear symbol notation for what's drawn. Now what I want to do is I want to draw the electron configuration. Realize that the number of protons and the number of neutrons have nothing to do with the electron configuration. The fact that it is non-ionized tells me that there is 8 electrons. If there are 8 electrons, I would start off with 1s2. Then I would go to 2s2. At that point, I've used 4 electrons. I have 4 electrons remaining, so I would say 2p4, and this would be the electron configuration. Now, I could also shorten that to the noble gas shortcut, where I would say helium, 2s2, 2p4. Both of those would be acceptable. Next, we have the proficient level question. And the proficient level question says, the electron orbital listed below are completely filled in. Is the Aufbau principle violated? Justify your answer using the clear method. So in this case, it says 1s, 2s, 2p, 3s, 3p, 3d, 4s. Now remember, when we drew this out, if you're looking at the Aufbau principle, you draw these orbitals out, and then you say 2p, 3p, 4p, and then you would begin with 3d and 4d. It fills in this order. So the first one I fill is 1s, and that's a check. Then I fill 2s, and that's a check. Then I fill 2p, and then 3s, check and check. The trick now, though, is that I actually fill the 3p, I fill the 3p orbital, and then I fill the 4s before I fill the 3d. So those should switch places because the Aufbau principle is violated. How I would justify this answer is I would say, yes, the Aufbau principle is violated. That's my conclusion. The evidence that I have is the 3d is filled before the 4s, and my reasoning is the 4s orbital is lower in energy than the 3d orbital. Next, it says, an atom with 34 protons has the electron configuration shown below. Write the proper atomic ionic notation. So if we were to look at this, we can start off with 1s2, 2s2, 2p6, and then I go here to completely fill the third orbital. So when I completely fill the third orbital, what I've referenced is I've gotten to a noble gas at this particular point. Or I filled 2 electrons plus 8 electrons plus 18 electrons, and then I filled another 8 electrons. So the total number of electrons that I've used at this point is, I believe, 36. If I added that up right, I have used 36 electrons, and I have 34 protons. Okay, so at this point you should realize that there's a difference between those two, and therefore you actually have to specify what the element is. So whenever you do this, the element that has 34 protons is selenium, Se. Whenever you look at the difference between the protons and electrons, you would say that there are 2 extra electrons, so you have 2 minus. So it's selenium 2 minus. Next, we have the electron configuration in the periodic table. It says there are similarities in chemical properties arise from the similarities in electron configuration. If you were to look at all the halogens, all of the halogens have a noble gas, S2P5. Okay, now the numbers change, whether it's 2s2, 2p5, 3s2, 3p5, 4s2, 3d10, 4p5, but they have this s2 and p5. So this explains why they react the same way, because they have basically the same valence structure. Yes, one has it in the second orbital, and one of them has it in the third orbital, but they are the same electron configuration, so they react the same way. They give electrons the same way. They accept electrons the same way. And so a lot of times they exhibit very, very similar chemical properties. Alkali metals. Alkali metals all have 1 valence electron in them, which makes it easy to give the electron away. So it's any orbital number, S1. So for example, hydrogen is 1s1. Lithium is 2s1. Okay? If you go down from there, sodium is 3s1, potassium is 4s1, and so on and so on and so on. Now, that excludes anything that's before it. So like, for example, lithium is not just 2s1, it's 1s2, 2s1, and so on and so on. Because of the ability to give 1 electron away, because they only have 1, alkali metals are highly reactive. Okay? Any alkaline earth metal have 2 electrons. So they have any orbital number, like 1s2, or 2s2, or 3s2. Because they have these 2 electrons right here, that fills the s orbital. Okay, so the s orbital is completely filled with 2 electrons. That makes it much more stable than an alkali metal, but it is still very easily able to give 2 electrons away. So because of that, these alkali metals are still reactive with most things. They will still tend to give their electrons away. Now we have the chalcogens. Now chalcogens are most of the time referred to as group 16. Okay, the chalcogens is kind of an antiquated name, but all the chalcogens have a 2 electron deficit because remember, everything wants to get to that noble gas structure. Everything wants to get to s2p6. Right now, it's any orbital number s2p4. So it's really easy for me to add 2 electrons to it to complete the orbital, but any chalcogen is going to be, can't be 1s2. It wouldn't work for 1s2, 1p4 because there's no p orbital in the 1. It could be 2s2, 2p4, 3s2, 3p4, 4s2, 4p4, and so on and so on and so on. So the chalcogens are also a reactive group, but they tend to react differently than the alkali metals. Instead of giving up an electron, they tend to take one. Halogens are group 17. Okay, they have a single electron deficit. They're all any orbital number s2p5, 2s2, 2p5, 3s2, 3p5, 4s2, 4p5, and so on. This makes them highly reactive electron recipients because if I were to add one more electron to it, it would complete the octet rule at that point. So they tend to receive electrons more than anything, and they tend to be highly reactive as well. Okay, now describe the chemical and physical properties of this element right here. If you were to look, it has a number and then it has an S2. That would make it an alkaline earth metal. Now that would mean that it's reactive, okay, but it's not nearly as reactive as alkali metals. So it also tends to be dull and soft and all those sorts of things. We'll talk about a little bit later. Next, it says pure sodium is mixed with pure nitrogen. There are no other substances present. Write the most likely ionic notation for each substance after they are allowed to mix. So whenever you have sodium, sodium is Na. It has a 1s, we'll just take it from, not argon, from neon, and says neon 3s1. Okay, and if you look at nitrogen, nitrogen is helium, and then it's 2s2, 2p3. Okay? At that point, if you look, it is very, very easy for sodium to lose one electron and become stable like neon. So we're going to say that it is most likely that sodium is going to be a +1. Okay? Because that would make it stable. Now, is it easier for nitrogen to take and lose 5 electrons or gain 3? And it's right, it's easier for it to gain 3 than it is for it to lose 5. So because of that, if it were to gain 3 electrons, that would give it a stable noble gas configuration as well. So if it gains 3 electrons, that would make it an A3-.